Hello viewers, welcome back to the course on matrix computation and its application. So, in the previous lecture we have discussed about the least square approximation, and in this lecture we also continue with that one. So, in the previous lecture we have discussed that if we have some data points, so suppose we have some data points and these data points are spread over the xy plane. So, we have taken n number of data points starting from here x1 y1 and this is xn yn, and then we have seen that if we want to fit a line, so we need a line that is closest to all these points, and we have found the error and minimizing this error. So, this is the line basically we have fit, that is we are writing y is equal to a plus bx, x1 y1 x2 y2, and in the end it is given xn yn. Then we have seen that based on this one, so for a line fit we have seen that we came across the matrix that is 1 1 1, and here it is x1 x2 x3 xn, and this is a b, and that is equal to y1 y2 yn, and we came across this system of equation where our line is y is equal to a plus bx. So, this is the line I have taken, and then we came across the matrix A, and this is x, and this is I can write as y. Now, also we have seen that based on this one we found that this system is inconsistent, and then we have talked about the projection matrix. Now, so based on this we have discussed about the projection matrix, that is P, and this is A transpose A inverse A transpose. So, this is my projection matrix which project the, or maybe I should take this as a B. So, we have seen that now P is of n cross 2. Now, we have seen that the rank of A is 2 because they are linearly independent, both the columns, and then we have taken the projections. So, suppose this is the plane, suppose I take a subspace, basically just showing like this one. So, it is a subspace spanned by columns of matrix A. So, this is the columns, and then let we have a vector. So, suppose this vector is not in the linear combination or the column space of A. So, suppose this is my vector B, and then we have shown that we are taking this projection of this on this subspace spanned by the columns of the matrix A. So, in this case its dimension is 2 basically. Then we have taken this projection. So, this is I have taken as a b hat, and this is the error, that is b minus b hat, and this is right angle triangle. So, and then we have seen that if I take projection matrix P, applying on B, I get B hat. So, this one we have seen. Now, I want to see what will happen if I want to take I minus P. So, if I take I minus P and apply on the vector B, which is the B vector I have taken on the right hand side, then I can write as a B minus PB, and this can be written as B minus B hat. So, if you see from here, it is B minus B hat. So, from here I can say that I minus P is also a projection, and so I minus P projects the vector B to the subspace orthogonal to the subspace spanned by the columns of A, because this is the subspace spanned by the columns of A, and I take the projection over this subspace. So, that is a B hat, and then we take the error terms B minus B hat. So, if I apply this one, I get B minus B hat. So, it means this is also a projection, and it projects the vector B to the subspace that is orthogonal to this subspace that is spanned by the columns of A. Now, so let us we talk about, so we have seen these things for the linear fit. Now, similarly, we can apply quadratic fit for the given data. In this case, I will assume that suppose we have y is equal to a plus bx plus cx square, and the data points are this one. So, this is, suppose I take this quadratic equation and I assume that passing closest to all the data point. So, in this case also, if you see, then I will get that y1 can be written as a plus b x1 plus c x1 square, y2 is a plus b x2 c x2 square like this one, and in the end I will get yn a plus b xn plus c xn square, and from here I will get the matrix. So, I will get the matrix 1 1 1, then here I will get x1 x2 xn and x1 square x2 square xn square, and from here I will get. So, in this case I need to find the value of a, b, c, and on the right hand side I have the values of y's that is given to me this way. So, also I can say that this, in this case I have a matrix that is of order n cross 3, and this on the right hand side. So, in this case I get the same system, only the condition is that the matrix now have the 3 columns made up of 1 xi and xi squares. Now, so this is my equation I have. Now, I know that this system, so I can say that now just I give the this 2. Now, the system 2 is consistent if all the data points lie on the quadratic. So, if all the data point lies on this quadratic equation, this one, then this system will be consistent and we get the solution, unique solution. But so, if the point lies on the quadratic equation, but in real world these points are spread all over the xy plane. So, these points are, as we have seen, that this is spread over the xy plane. So, in that case we say that the system 2 is inconsistent, and then we will find out the same way that we multiply by A transpose A, and I will write x A transpose B. Now, if you see from here, so this is the equation number 3 and it is called the normal equations. Because if you take the A transpose, then A transpose I can write as a 1 1 1 x1 x2 xn x1 square x2 square xn square, and similarly it is x1 x2 xn xn square x2 square xn square. Into x, that is A B C, and A transpose is x1 x2 x3 xn x1 square x2 square xn square, and this is my y1 y2 yn. So, I can write this equation 3 in this form. Now, if we start doing the multiplication of this matrix, then you will see that it will multiply. So, from here I will get a matrix. So, this matrix is basically 3 cross n and this is n cross 3. So, I will get the 3 by 3 matrix. So, if it is, I am taking this one, so you will see that it is n number of times taking the summation. So, it will be n. Then I am taking first column and this row, then I am multiplying this first column with the second row, and I will get summation of all xi's, and then this one I will get the summation of all xi square. Then I will take the second column here, so it will be summation xi summation xi square, because x1 will multiply by x1, x2 is multiplied by x2 like this one, and this one I will get x1, so it will be xi cube, where summation is over all over from I to n. So, this is from I to n in all the summations. Similarly, I can take the summation, So, now I am taking the third column. So, it will be x I square x I cube, and this will be summation x I power 4, and this is a b c. And on the right hand side, this is again 3 cross n, and this is n cross 1. So, I will get a vector of order 3 cross 1. So, I can write from here. So, I am taking this summation. So, it will be summation of y i's, because multiplying this one, it will be the summation x i's y i's and summation x I square into y I. And this equation 2, I can write this as equation number 4. So, if you see from here, then I can write from here, I multiply by this, so n, and you know that if you see from here, then this matrix is a symmetric matrix. This and this value are symmetric, this value is also symmetric. So, from here I can write that summation n a plus b summation all x I plus c summation x I square, because it is x I square, that is equal to summation y i's. Now, I can write like this one, a summation x i's plus b summation x I square and c x I cube, and this is x y. So, you can see from here that if I multiply this by the x i's, then I will get this equation. So, third equation will be summation x I square plus b summation x I cube plus c summation x I power 4, and this is my x I square y I. So, this is, if you remember from the least square method, what we can be draw from the scientific computing or numeric analysis way, then if you remember, then this is equal to the normal equation. So, these are the normal equation, and then we can solve this one to find the value of a, b, c. So, this is the way we can derive the normal equation through the linear algebra. Now, let us take one example. So, in this I am taking one example. Suppose we have the data point that is given to me like this one, 0.1, and this is minus 0.18, 0.2, 0.31, 0.3, 1.3, 0.4, 2.48, and the fifth point is 0.5, 3.73. So, these are the data points given to us. So, then our question is find the best, first one line fit, and the second one is quadratic fit. So, this is the question. Now, so I can, so my x is 0.1, 0.2, 0.3, 0.4, 0.5, and my y is minus 1.03, 2.48 and 3.73. So, now if I take the line fit, now the case 1, best line fit. So, in the because this is the least, we have the error and that error is the least one. So, that is why it is the best fit, and in this case I will choose the line y is equal to a plus bx, and then based on this one I will get the matrix, that is 1 1 1 1 1, because 5 points are given to me, and these x are 0.1, 0.2, 0.3, 0.4, 0.5. This is my AB, and on the right hand side we have 1.8, 0.31, 1.03, 2.48 and 3.73. So, this is my line fit, and I will find the solution of this one. And the second one is we have best quadratic fit. So, in that we will get, so basically this is 5 cross 2 matrix, and I will get and this is the square I will get. So, I will get 0.1 square, and I will get A, B, C, because here I am consider y is equal to a plus bx plus cx square, and on the right hand side I will get the same y. So, again I can write minus 0.18, 2.48 and 3.73. So, these are the two equations we need to solve. So, if we solve it manually, then it is going to take much time from here. So, we can solve this with the help of MATLAB or Octave. So, let us do with that one. So, first I will write a script for this, and I will save this script as maybe I can put it on the desktop, and I will write it as least square. So, this is my script file. So, in this case, so first of all I want to write that I want to clear all this variable and then CLC. Now, I need to define all my x points. So, I will just first take the x coordinate. So, x I can write as 0.1, 0.2, 0.3, 0.4, 0.5, this value. Now, the y is given to us, that is minus 0.18 and 0.31, 1.03, 2.48 and 3.73. So, these are the y coordinates we have taken. Now, whatever the points are given to us, now I want to plot these points. So, I will write the plot x, y. So, I just want to plot this one with points. So, I just write k means black star and this one. So, this is now if I suppose I just stop here and I run this one. Okay, so, this is the change directory. So, this is my x coordinates and this is the y coordinates and this is my plot. So, you can see that we have a 5 points. So, this is the points is given to me 1, 2, 3, 4, 5 and all these point if you see that does not lie. So, this point they do not lie in a line. So, if I take a best line fit, then definitely the system will be inconsistent. We have to take the line which is closest to all this point. Similarly, so one line I can take like this one and the another quadratic will be the another type of parabola which is also not passing through all this point, but going very close to this one. So, this is the figure I have just taken. Now, we continue with our code. So, this is the plot I have taken till here. Now, I want to define, first I will take the things for linear fit. So, I can write for line fit. So, I take a matrix A. So, that matrix I know this is it is 1 and x 1, then again 1 and x 2, 1 x 3. Because I am writing this as a in the columns, and in the end I will get x 5. So, here I will get the matrix with the first row as 1 x 1, second row is 1 x 2 and this one. So, this way we are able to write the matrix A. Now, so I can write this one as for the line fit and similarly I can write for quadratic fit. So, in the quadratic fit I will again write the matrix. So, let us I write this quadratic means I just should write QA. So, this is my matrix, and if you see from here I can write the same matrix here and I will just copy this. So, Control C, so here I can just take these values. Now, if you see from here this is 1 x 1, now I have to put here x 1 square. So, that only the change I have to do. X 2 x 3 square, x 4 square and this is x 5 square. So, this is my quadratic fit. Then I write the right hand side vector. So, I just write b is equal to, so that is my basically y. So, y I have written in the row form. So, I will just take the transpose of that one. So, this will be my y. Now, so after this one I just want to check whether this line fit or the quadratic fit are passing through all those points. So, for that one I write a matrix AA. So, just write first A and then B. So, this is my augmented matrix I am writing here, and similarly I am writing the augmented matrix QAA for quadratic. So, that is I am writing here QA and then B, because everything is same except the matrix on the left hand side. Now, first of all I want to check the rank. Now, after augmented matrix I just want to find out the row echelon form. So, row reduced echelon form. So, I just write R row reduce of AA, just I am writing. So, it is a command that row reduce echelon form of, so it will give you the row reduce echelon form. Similarly, I can write row reduce of QAA. So, that is also I can write this one. So, from here I will get the row reduced form, and if you want to check you can check the rank of also. So, I can just check the rank of A. I can write this of the matrix A. Similarly, I can find the rank of QA, and that is rank of matrix QA. Now, from there you will see that the rank will be different. So, this will be inconsistent. Now, after this one I define the matrix A transpose A. Now, I want to define the matrix A transpose A. So, A transpose A, I just write short form A transpose A. So, this matrix I am writing as a variable. So, from here I am writing the matrix, this matrix. So, now I am writing from here matrix A transpose A. So, this one I am writing. So, that is I am writing like this one ATA. So, what I am going to do here, I am just taking the matrix A, taking its transpose and then multiply by A. So, this is the matrix I am getting, that is A transpose A. Similarly, I can get QA matrix, then the transpose QA. So, this is matrix I am writing here. So, that is QA multiply by QA. Okay, so, we are able to find out the A transpose A matrix here. Now, after doing this one, so I am writing from here, this is X is equal to A transpose B, and from here I will get A transpose A inverse, then A transpose B. So, I will get this answer. So, this is my X hat. So, I will write this here. Now, I can write here inverse A transpose A. So, So, I am writing here inverse of ATA, because that matrix will be invertible, no problem. Similarly, I can define inverse of QATQA. Just I am writing this name, and that is also I am finding the inverse of QATQA, this one, and here I am writing, just I am giving the name, this name I am giving. So, let us try to run this one and see that if we have made any mistake. So, I just run this one. So, everything is okay. So, this plot is okay, and if you see from here, so I am getting this matrix. Now, we have started from here. So, I have this x coordinate, this y coordinate, and this is my matrix A, and this is my matrix QA, that is for the quadratic I am taking, and then I have defined from here, this is my right hand side B. Now, you can see from here I have defined the AA matrix. So, A just I have taken the augmented matrix, and QA is I have taken the augmented matrix, and then I found the rank row reduced echelon form. So, this is my row reduced echelon form of AA matrix, and you can see from here that its rank is 3, but the rank of matrix AA is 2. So, this is inconsistent. Similarly, the rank of this matrix is 4, and the rank of this matrix, the matrix we are taking, is 3. So, this is inconsistent. So, you can also check that the rank of matrix A is 2 and the rank of matrix Q is 3. So, this is the inconsistent matrix. Now, after that I have defined ATA. So, A transpose A matrix I have defined. So, this is 2 cross 2 matrix, and this is the values. Similarly, I have taken the QA transpose QA. So, this is the matrix 3 by 3 matrix I will get, and you can check that this is a symmetric matrix, positive definite. So, this is my matrix. Then I have defined the inverse of this ATA. So, this is the inverse it is coming, and here it is the inverse of QA. So, that is the quadratic, corresponding quadratic. I have taken the inverse, this value is coming. So, up to now it is okay. So, I can define the next. So, now I want to find the solution of this one. So, after defining, I want to find the x hat for A, and then x hat for QA. So, let us define the x hat. So, this is I am going to define the x hat, and this is for the corresponding line. So, I just take L, and that will be equal to the inverse I am defined ATA. So, this is the inverse we have defining, multiply by the transpose of A, because that we have to define, star the B on the right hand side. So, that will be my x hat in the terms of the line fit. Similarly, I can define the x hat in the terms of quadratic fit, and that is also I have to define the same way. So, it is inverse star QA, taking this value. So, I have taken the inverse of A transpose A, A transpose B. So, this is what we are defining, A transpose A inverse A transpose B. Here also I am taking, so I am defining this by L, the line, and I am defining here by the quadratic x hat. So, this is also I am defining A transpose B. So, now this is my x hat L and this is my x hat Q. Now, after defining this one, so I am able to find the solution. Now, I have to define the line and the quadratic. So, let us define the line. So, I define, because y points are given to me. So, I just define the line here now. So, I just write the line fit is, so the line fit is, so here I am defining y, or maybe I defining L, that is my line. So, line means I have to define A plus Bx. So, x hat L, so I can take from here x hat L first coordinate. So, that will be my A plus x hat L 2 times multiplied by x. So, this is my line L. And similarly, I can define Q, the quadratic. So, that will be x hat Q first coordinate plus x hat Q second coordinate multiplied by x and plus x hat Q 3 multiplied by x square. So, this one I can just write like this. So, this is my quadratic fit and that is my line fit, and now I can plot these things together. So, what I am going to do is now I will take hold on means it will hold the plot in the above, and then I can write plot. So, I can plot x corresponding L with, I just define by blue color, and x with Q, and then I define by red color. So, this is I am doing here. So, let us save this one and then run this. So, just first I will check these things. So, now up to now we have seen that, so this is my XL hat. So, the value is A is minus 1.52 and this is B is 9.99, and for the quadratic the value of A is 0.93980, B value this one and C value this one. So, the line is passing, so this is my coordinates of the line that is passing through the given point, and this is the coordinates of the quadratic passing through the whatever the coordinates we found from the given quadratic form. and if we see this one, now this is the corresponding plot. Now you can see that these star points are there. So if I take a line is blue color, so that is the best fit, and this is going close to all these 5 points, and the red one is the quadratic. So you can see that in the case of quadratic, it is passing exactly from 3 points and going little bit away from these 2 points, but the line is passing through only 1 point and going away from these 4 points. So you can see from here that in this case the quadratic is I think it seems better than the linear fit, because these points are going very close to the quadratic equation. So this way we can plot the all the 3 plots together in one plot by the command of hold on. So this way we can define the corresponding, or we can write the code for finding the least square method. So after doing this one, you can also check about the projection matrix, because we also define the projection matrix. So I will just show you that we can also, I have solved this one, but these things can also be solved with like this one. Here what we do, we define projection matrix P taking B, so it will get B hat, and then I can solve it A x hat is equal to B hat. So this way we can solve. So by this way also we can solve the given system, and after that, so projection matrix, maybe just I can write the projection matrix. Let us define that one also. So writing the projection matrix. Here. So I can define my P is equal to, so I am writing the projection matrix first for line L, because it depends upon the matrix. So projection matrix for the line. Now if somebody is becomes confused, then they can also write here the some comments, and like this one. So I can write here that line fit. Here I can define as quadratic fit. So similarly I can define here the projection matrix. So projection matrix, you know that for the line is, I just take A matrix, putting star here, and then I am writing the inverse of A transpose A. So it is, I am writing here inverse of A transpose A star, then A transpose star. So this is my projection matrix. So projection matrix is A transpose A inverse A transpose. So this is my projection matrix, and I am writing this one here, and if you want to check, then you will see that the projection matrix is a symmetric matrix, and if you see, then its square, and its square will be also the same. So this one I can just save and I just run this one. So, I will get the similar things here. So, you now I have, this is my the projection matrix in the case of 5 points. So, it is 5 cross 5 matrix, and then you can see that this is just the symmetric matrix you can see from here, and if I taking its square, then this is PL square. So, PL square is also equal to PL. You can see that it is 6 point this 10 raised to power minus 1. So, that will be 0.6, it is 0.4, 0.2, it is e raised to power minus 16 means it is 0, and here it is 0.2. So, you can also verify that PL square is equal to PL. So, this is the my basically the projection matrix, and now I can even check from here that my PL star projection star B. So, that will be my B hat basically. Maybe I can just write here, and now if I write PL star B, so this is my B hat, and now from here you can see that B hat is this value. So, now if I apply this one PB, so this is my B hat, and now I can solve this AX hat is equal to B hat, and then I will get the solution. So, you will get the same solution as this one. Maybe I can write here the some value I just get x, so that I can write a backslash and the answer. So, this is the answer what I am getting, and this is the my x hat. So, x hat is minus 1.52 and this is 9.9, and if you see this is also the same, this value minus 1.5 and this value. So, you can verify that these both are coming same. So, either you can go directly by the normal equation, or you can go by the projection matrix and then you solve the system this one. So, both the ways you can find the same solution, and this way we are able to do this. So, the same way we can go for cubic, for fourth order fit. In that case only the calculation will be more, and then you can use this type of code, and then based on this one you can find out any fit, maybe it is. So, you can find the nth degree polynomial fit using the same code. So, it is just the a small code we have made, that how we can extend this code for the other type of polynomial fit also. So, I think now we stop here. So, in today's lecture we have discussed about the least square method, and we have shown that for a given data how we can define the line fit and the quadratic fit, and then we have written a code in the Octave, so that using that code we can find out a line fit or a quadratic fit, or maybe we can extend this one to any polynomial fit of degree n. So, I hope that you have enjoyed this one. Thanks for watching. Thanks very much.